Hello everyone. In this video, we'll be solving a numerical problem based on the boundary value solution to Laplace equation. The given question says two conducting cones are given and the two are of infinite extent separated by infinitely small gap at r equal to 0. So I can graphically show what it is saying. One cone and another cone. These two are not touching each other. Some infinitely small gap is there at r equal to 0. And one is at an angle of pi by 10, another is at an angle of pi by 6. So the two boundary conditions are given. I'll be writing the boundary condition. At angle theta pi by 10, voltage V equals to 0 volt. And the second boundary condition is at angle theta equal to pi by 6, voltage V equals to 50 volts. We are asked to find V and E between the cones. So we have to find first V, which is a function of theta, and electric field intensity. So we have to start solving for this in spherical system of coordinates. Now we have to consider Laplace equation, which is del square V equals to 0. Now, starting from this Laplace equation, applying these boundary conditions, we will find what is V, which is a function of theta. We will write the Laplace equation in spherical system of coordinates. And also in this case, V is a function of only theta, which means differentiation with respect to r and differentiation with respect to phi is going to be 0. And only this term is non-zero in this del square V function. So I'll be writing 1 by r square sine theta, dou by dou theta of sine theta into dou v by dou theta. So this partial differentiation can be now written as ordinary differentiation because V is having a single dimensional potential function only. Now this 1 by r square sine theta, if r square sine theta is multiplied with the right hand side, that will be 0. I'll be getting d by d theta of sine theta dv by d theta equals to 0. Now I have to integrate with respect to theta. So to remove the differentiation once, I'll be doing integration with respect to theta, which will remove differentiation of theta. So left hand side will be sine theta dv by d theta, and the right hand side integration of 0 is 0 plus integration constant c1. Now this sine theta has to be brought to the right hand side, which will give dv by d theta equals to c1 by sine theta. Now one more time integration with respect to theta will give me what is the potential V, which is a function of theta. So the left hand side will give V and the right hand side is integration C1 by sine theta d theta, and 1 by sine theta integration with respect to theta will be logarithm of tan theta by 2. This is the integration formula. So by using this formula, we can write potential V as C1 logarithm tan theta by 2 plus C2. So this is the potential function V. Now we need to apply the boundary conditions. Let me take the boundary conditions and apply the boundary conditions to find the constants C1 and C2. So this is the boundary condition. Let us take this boundary condition and we will be writing the potential V, which we have got, which is C1 logarithm of tan theta by 2 plus C2. So this is the potential, which is a function of theta. So now in this, we have to apply these set of boundary conditions to get C1 and C2. First boundary condition, if I apply, V will be 0 equals to C1 into logarithm of tan theta by 2. Here theta is pi by 10. So theta by 2 will be pi by 20 plus C2. And applying the second boundary condition, you will be getting 50 volts equal to C1 into logarithm tan. Here pi by 6 is there. Divided by 2 will be pi by 12 plus C2. Now what you can do, you can take out calculator and find these values. These are the radian values. Use your calculator in radian mode and find tan pi by 20 and natural logarithm of that tan pi by 20. For this natural logarithm of tan pi by 12, all these should be taken in radian mode. And when you solve for these two equations, you will be getting the constant C1 and C2. I'm leaving those for your exercise. I'll just give the values of C1 and C2. You can complete it using the calculator. So C1 is going to be minus 95.09 and C2 is going to be 175.24. You can verify this by solving these two equations with two unknowns. You can directly use calculator and solve also. But you must use the values of theta here in radian, so use the calculator in radian mode. Now, substituting this, we will be getting the potential function. So V, which is a function of theta, is C1 times, that is minus 95.09 times logarithm of tan theta by 2 plus C2, which is 175.24. So this is the potential function and the unit must be given as volts. Then we should find electric field intensity. So the electric field intensity is negative potential gradient. We have to write the potential gradient formula in system, which is spherical here, which is dou V by dou R A R cap plus 1 by R dou V by dou theta A theta cap plus 1 by R sine theta dou V by dou phi A phi cap. Here in the given potential, it is only a function of theta. So differentiation with respect to R and phi will be 0. Only theta differentiation will be left. So doing that differentiation, we'll be getting E as minus 1 by R. Differentiating this with respect to theta. So constant minus 95.09 will be there as it is. Differentiation of logarithm tan theta by 2 will be 1 by sine theta, which we have already discussed, and 1 by sine theta. Then the second term is constant. Differentiation of constant is 0. We'll be getting A theta cap. So we can write this electric field intensity expression as minus into minus. You will be getting a plus over here. So plus 95.09. One clarification here, the C1 value is not, the C1 value is not minus 95.09, it is plus 95.09. You can verify this solution using calculator, and thereby here voltage function will be plus, and here again it will be plus. So you will be getting electric field expression as minus 95.09 by sine theta, R sine theta, A theta cap. So this is the electric field intensity expression. So you can give the unit for electric field intensity vector as volt per meter. So we can perform this by taking the del square V function in spherical system of coordinates, the the coaxial cones with one angle pi by 10, another angle pi by 6 in radians are given. We have made use of the boundary conditions in the expression for V, which is a function of theta, solving for the constants and substituting the constants will give the voltage, which is a function of theta. And by applying this formula where electric field intensity is negative potential gradient, we have got the expression for electric field intensity as well. I hope you have understood this problem. Thanks for watching the video.